Hello everybody and welcome to MME 2305 Material and Energy Balances. This is another kind of small, shorter video. Again, kind of trying to chop up some of these topics into little bits to make them easier to grasp and understand. The topic we're going to be talking about today is heat of mixing. All right, one thing that I'm going to talk about that's not really in the Felder and Rousseau book is heats of mixing, and particularly heats of mixing for metals. And so heats of mixing, you get some heat when you dissolve one substance into one another. And so if you've ever mixed water and alcohol and you notice that there's some heat, well, that's the heat of mixing. And if you make like a mixed drink or something, there's some heat, the ice tends to melt a bit quicker than if I just put water of the same temperature in there. And so that's heat of mixing. Think of an alloy. And so when you mix different metals together or whatnot, and you get different phases, well, there's a heat of mixing associated with that. Another term that comes up when we're mixing metals together is amalgam. And with an amalgam, you don't get distinct phases. An amalgam is just clumping a bunch of metals together and trying to use that as a material system. And you typically don't get secondary phases or another phase when you have amalgams. And the most common thing I can think of, and maybe you guys have been exposed to amalgams in other classes, is dental fillings. And this is kind of a thing of the past, kind of these mercury-based metal dental amalgams, where you've mixed mercury with several other metals and sometimes silver and even precious metals to make kind of fillings for your cavities in your teeth. So what we're going to do is we're going to look at the heat of mixing for simple alloy system. I've gotten these. When we think of heat of mixing, so if we plot heat of mixing for an alloy system, the plot of this is ideally symmetric and parabolic. And if we think of a binary phase diagram or eutectic phase diagram, we kind of see some of those details, and I'll point that out to you in a bit. When we have two things coming together and we're calculating the heat of mixing, we kind of refer to this as the regular solution model. And I'll explain a little bit about where this parabolic nature comes from. You have XA and XB, so metal A, metal B. You can write one in terms of the other, so you effectively have an x squared function. And so the x squared function, you can plot this stuff on Google, it's kind of cool. This is simply a parabola. It's not quite this simple, where you have the I guess minimum at the 0 point, or the 0 basically. One thing about omega, it's a constant and it's independent of temperature. When you rewrite one of the compositions in terms of the other, so we can rewrite fraction of B in terms of fraction of A, so we get 1 minus x sub A. We can rewrite our heat of mixture equation as omega equals this quantity, xa minus x squared of A. So we have our x squared term. And if you notice, we have our parabolas, and the maximum or minimum is at 50% composition. So it's actually kind of cool. I'm just kind of seeing it mathematically. And whether it's a maximum or minimum depends upon what the omega value for your alloy system is. And here's me going out toilet paper shopping. The maximum minimum occurs at the 50-50 composition depending on omega. So that's kind of the key takeaway of this little exercise. If you look at phase diagrams in general, so they're usually temperature versus percentage, but you can relate your given temperature with the heat of mixing at a temperature X. And they should correlate pretty well. And if you look, you're trying to get this kind of almost parabolic-like behavior here. So here's a minimum, a maximum of this curve would be here. So you kind of see this ideal solution equation or artifacts of it on phase diagrams. It's kind of cool. Here's another example of another binary phase diagram, and so still kind of that same behavior. We have a problem involving gold and silver and copper, excuse me. Coin silver is 100% by mass copper and 90% silver. You're working in a foundry and you want to know what the molar heat of mixing of liquid coin silver is at 1150 degrees C. Here's an example of the data that we care about when we're solving this type of problem. And we have different heats when it's solid and different heats when it's liquid. And one thing to point out is that even though it's an X notation, this is actually molar percent. This is actually a pretty bad table because it doesn't give you the units on the table. But these is all calories and not joules this time. So this is calories per mole, and this is mole fraction versus mass fraction. And so we've been given mass fraction on the problem, so we're going to have to convert that to mole fraction, and we all know how to do that. All right, we're going to take a quick look at the heat of mixing problem. Just to kind of reiterate, we're interested at making coin silver, which is 10% by mass copper and 90% by mass silver. Just to kind of reiterate, the notation's a little different. This came from a totally different source than we've been using, but this is in mole percent, actually mole fraction. And the value for the enthalpy of mixing here is in calories. And so I wanted to kind of make that clear, and let me try to de-blurify this just a tad. Okay, so calories and mole fraction. This is atomic percent copper, and I'll work it out, but for atomic percent, when we have the mass percentages we're given, we're in between 0.1 and 0.2, and 1423K is roughly 1050 C. Wait, which temperature did I specify? 1150 C. Yes, my bad. So we're actually very much high. So we're totally in the liquid regime. So the values that we become interested in are related to these two here. But there's some things we have to do first. So this kind of ends up being a two-step problem. And so step one, we're given mass fraction. Where it said the problem said 10% copper, 90% silver. I told you that this is mole fraction. So the first step we have to do is convert to mole fraction. And we know how to do this. We're old hands at this now. We kind of need to know the atomic mass. So remember, if we're going from mass fraction to mole fraction and vice versa, we need atomic weight or atomic mass, depending on the words you're using that day. For silver, argentum, we have 107.87 grams per mole. And for copper, we have 63.55 grams per mole. We know our mass fraction, so we can take a basis of 100 grams based on the given information. We can calculate our number of moles of copper is based on this 10 grams of copper. So if you remember, we were 10% by mass copper, 90% by mass silver, excuse me. So 10 grams, and we have 1 mole of copper is 63.55 grams, so grams cancels, and we're left with 0.157 moles of copper. And we need mole percent or mole fraction. So to get mole fraction of the copper in all of this, we need also to calculate the moles of silver. And so number of moles of silver is 90 grams. And 1 mole of silver is 107.87 grams. And so that equals to 0.834 moles of silver. And hopefully this isn't too blurry. So we want to get our mole fraction. So our XCU, so I'm kind of changing notation to match the table. So X copper is 0.157 over the total. So if you remember, the total is 0.157 plus 0.834. This is the copper, this is the silver, and I get 0.159, and you can follow along. So the mass fraction, or sorry, mole fraction, these notations, excuse me, okay, so now we have 0.159 is our mole fraction of copper. If I look at the table, I don't have that exact value tabularized. We don't have our fancy Excel table, so I can't just put in the mole fraction of copper, so we can interpolate. And hopefully you guys remember linear interpolation. And we have some values, and so off this table now, when our X of copper, our mass, our mole fraction is 0.1, we have a heat of mixing of 455. And when our mole fraction of copper is 0.2, our heat of mixing is 748. Okay, so I hope you guys remember linear interpolation, because we don't know what the heat of mixing for, what did I calculate the value of? 0.159. The heat of mixing is a big fat question mark. Okay, and it got a little blurry. It's what? So we don't know what the heat of mixing is. Hopefully that's a little better. Heat of mixture when our mass fraction is 0.159. And the linear interpolation question, or equation is, I'll write it out for you. So it deals with x and y, and so y minus y1 over x minus x1 equals y2 minus y1 over x2 minus x1. And you can look this up. This is kind of a skill that hopefully you guys have retained from another time, but if not, check it out here. So this is a linear interpolation equation. This is the interpolation equation. And I know you guys are dealing with the blurriness of my equipment. I'm trying to get new gear before the semester's over. But anyway, we have this equation. We can take the heat of mixtures to be our y, and we can take the mole fraction to be our x. And so we know that one of these is going to be x1, x2, y1, y2. This one's going to be x, and then we're going to solve for y. Okay, so we can rewrite our equation as y equals to y1 plus, in parentheses, y2 minus y1, and then all multiplied by this value, x minus x1 over x2 minus x1, or x2 minus x1, and just plug in chubs. So we're going to solve for y. This is going to be y, the heat of mixture, when our mole fraction is 0.159. Y1 is going to be 455. Y2 is going to be 748. So we can say this is Y1, Y2. This in the same hand, I guess, X1, X2, and then this is just X. Okay, and so Y, Y1 is 455 plus Y2 is 748 minus Y1, which is 455, and then multiplied by this fraction, I guess I'm going to call it. X is 0.159 minus X1 is just 0.1. So I'm going to work out very nicely. And then X2 minus X1. So X2 is 0.2 and X1 is 0.1 again. And plug that into your calculator. You're going to get a heat of mixture. And hopefully you can read it. A heat of mixture of about 628 calories per mole. And I should have put calories per mole here. All right, so that is the answer. That's how you work that problem out. Oh my. It's the end of the lecture. If you have any questions, you can email me at drobertson@utep.edu.